Hello, Royal.
Hi Robert, how are you?
Nice to meet you. I am very happy to be in your facilities. And I am totally nervous to see what you are doing here. So let me see how to build a loudspeaker.
Well, you're welcome. We always love having visitors, so please come in and I'll show you.
Okay, thank you very much.
And thanks for coming so far to see us. So this is the factory that we built in 1988 when we started manufacturing for Rowan, but also developed the speakers for Studa. So in those days, Alain knew that it was going to be, he had quite a bit of production to be done, so he built this factory that's been here for the last 30 years. And here you can see kind of the first products that were developed.
Yes.
So this is the first speaker that he produced, two-way speaker, closed cabinet. Then he moved on to more complicated speakers, three ways, all passive for the moment, no amplifiers in it. So these were used for hi-fi, but also started being used a little bit in studios and broadcasting. Those are the last passive models that we made here.
Which amplifiers drive that loudspeaker?
There's no amplifiers here yet.
No, but which were the usual amplifiers?
Different, that depended on the customer.
You sell it when with an external amplifier or recommend something to the buyer?
That depended mainly on the reseller who decided to match them with amplifiers.
Okay.
And then we did also a lot of public address speakers where we haven't got any cabinets here, any boxes here, because they were very bulky, very big, but this is the type of driver we used to use in here. Big horns, of course, that you can see here, with the engines that go with it. So yeah, this is what we did until, I would say, 88. And then we developed active speakers for the company Studa.
These are also passive.
So here we have passive speakers. So this is like small speakers we use in PA that were passive, and then kind of evolution of it that had active. So this is with an amplifier that we developed for Studa, and these were the first type of passive ones we made. So we had small ones like this, but also much bigger one, three-way systems that we made here. Until Studa was acquired by an American group, and they decided to discontinue the contract we had for manufacturing, and they bought their own. They used their own speakers. And since then, well, we manufacture our own and sell our own internationally. PSI Audio.
Great.
So this is more administrative office where we've got to do all the main admin. Here we have. Alain and Nicolas working on a new design also.
Yes.
So this is all drawings of new bits and pieces of speakers. I can't tell you too much about this yet.
Well, if you see only that, you won't able.
Yeah, you can't see much on that.
They have some measures.
Yeah, lots of measurements and.
Yeah, we have to find a lot of components and. So everything fits together.
Okay.
And this is the next technical office. This is, well, here let me introduce you to Christian Martin, who's our principal engineer and technical director, who's been here for 25 years. Came here straight after he graduated as a telecommunication engineer, like you.
Yeah, he's the brain, the designer.
Yeah, he's the brain.
And the most important person.
Yeah, everybody's the most important person, but he's the most important of the most
most. The most.
Yeah.
So he's with some calculations here. Wow.
Yes, we do a lot of. We don't. On fait pas du numérique, mais beaucoup de modélisation numérique.
So of course, all our products are analog, but we use a lot of digital technology to do the modeling, and that saves a lot of time.
And
calculate. Look at this.
All the filter. Yeah. Okay, if you want.
So we have a lot of electronic tools like this and
Yeah,
software.
This is
to get as close as possible.
We develop our own system de calcul pour toute la partie filtrage. Quand on mesure d'abord les enceintes en position et puis ensuite on va simuler toute l'électronique. Et là, bon, là on voit ça doit vous intéresser là, les high pass, les low pass, the
all pass filter.
Les réponses en phase.
So these are all tools that we developed here.
Yes, we developed after we test in anechoic chamber and we can see our model are correct.
You do the models and then the prototype and then you test it.
And it's fit exactly.
And sometimes you must to have some hands calculation and sometimes in computer. Okay, that's very nice.
Yes, in an active speaker you have a lot of components, so you cannot calculate everything here. Yeah, it's a lot of work, but it's work.
Great. Thank you very much.
Thank you,
You're welcome. Bye bye. Good visit.
Let me take you downstairs to the workshops now, where it all happened.
And the demo room?
Demo room, you want to see that now?
Yeah.
So, follow me. So this is the basically the range of speakers that we manufacture now from the A14. That's the smallest model. This one's very much appreciated when space is an issue. So typically OB vans and places in multi-channel. So we've done systems with 30.2 systems. So very much appreciated when there's not much room. Then we have the A17 here. That's a bit bigger. So this is already used mainly home studios and small studios as a near field, and very impressive by the punchiness and how much bass and tight response comes out of such a small cabinet. Then we go on to the A21. That's already bigger, and this one's appreciated for the precision and lots of people doing. Producing music use these, recording they use them a lot in broadcasting. And then we have our flagship, that's the A25. That's our three-way system and the pinnacle of our range. And this model is used in places like the Bolshoi, the IRCAM in Paris, lots of radio stations, ZHDK, Cambridge King's College Choir. And this is the direct evolution from this grandfather we can see here, that we still repaired. So this is one that we're just testing, having repaired it after already 20 years of use or something like that. Yeah. So this is where we have a showroom. It's not a perfectly acoustic treated room because we want people to hear how good our speakers are, not how good our room is. That's the idea.
Okay.
And this is I forgot to present this one. This is the A215 215, and this one is developed as a mastering speaker. So it's a very good mastering. It's very useful because it stands alone. It goes down very low also in frequency, so you normally don't have to use it with a sub. And the directivity has been optimized to use in more of a living room or environment, so more like a
home cinemas.
Yeah, home cinema works well, but also mastering type of room more than a typically mixing studio. So the idea is they're all perfectly. We try and have a perfect frequency and phase response in all of them. But when you go from a small model to a bigger one, it allows you to go low in frequency. It allows you to have a bigger pressure, higher pressure, so higher SPL. And it also allows you to keep tighter tolerances around the specification. So from a small model to a bigger model, you will gain in low-end frequency, SPL, and accuracy. But otherwise they all mix and match, and you can use any of them. You can mix and match them in any multi-channel system. So you could, for example, have these in front in a 5.1 and these at the back. It would work perfectly. That's also a big advantage. You don't have to have the same speaker everywhere.
And I see that there is also the AVAA.
AVAA, yes, we can see one. Well, you can see one that's open here. I can show you this a bit more. So normally there's a protective grille in front. The protective. Oops, sorry. I can put this up again. So normally there's a protective.
It is only protective. It has not other.
There's a grille around that protects it. So here we've taken it off. Okay. And so this has got a very fine resistance and a very well determined acoustic resistance. And the idea is you have a microphone here, then you have this resistance, and behind that you have a driver that's going to impose a very low acoustic impedance in front of this grille. And that's basically how it works. But you only have a few centimeters between the microphone and the counter reaction on the driver. And this is the time you have to have it accurately in phase. So you have to be very quick with all the transfer function. And this we managed to achieve much better, of course, with analog technology than with digital technology. So basically, we're very proud to be able to manufacture this with analog technology, and it's better, more efficient, and more stable than any digital technology.
All your equipments are analog?
Oh yeah, everything that we do is 100% analog, by choice, of course, because digital technology is great if you have to memorize or information. If you want to, like a song or music, it's a lot easier recording it with digital technology within analog technology. But then between the entrance of the electric signal into a speaker and the acoustic signal coming out, nothing's going to change, and it's going to stay like that during the whole lifetime of the speaker. So you might as well fix it in analog technology. There's no need to have a double conversion back to digital and back to analog again, and just keep it like that. And you gain also a lot in latency also between the time, which is important when you're doing recording, post-production or mixing. Not so important if you're listening to music at home. So that's the reasons we do analog technology, and we've kept this know-how, and you shouldn't think of analog technology as being vintage and old-fashioned. There's some very advanced high-tech analog system that has the advantage of not needing any conversion and no latency. It's very useful. And don't forget that sound is analog, ears are analog, and so most of things in nature are all analog. It's only when you want to store them in memory and process them that you have to go into digital. Otherwise there's no real reason.
Okay.
There we go. Let me show you where we manufacture all of these downstairs. Yes. And you can see the degree of precision and know-how that's necessary to manufacture all of these speakers. Here we have a little area we can have coffee.
Yeah.
So we have about 10 people working here, and what's interesting is there's at least 25 different jobs that are necessary.
And they are not right now here because this is too late to Switzerland.
Yeah.
Only the designers.
Only the designers, yeah. No, the manufacturing is now, stopped, yeah.
Okay.
But I can show you around and you can understand most of it. So yeah, as I was saying, there's about 10 people working here, and we have at least 25 different jobs. So there's everybody does a lot of different jobs, and that's what keeps it interesting. This is our woodwork and metalwork shop, where we do a lot of prototyping and little things, but also little bits of production like these are things very simple, but we do them all here because we can. And each time we ask for a quote, to outsource them becomes more expensive than manufacturing them here. And one thing that's also very important is we want to keep the entire know-how of our manufacturing in-house. So it's important to know how to do these things. There's little elements like this. These are plastic potentiometers that we have to fix a little O-ring in it. So this has to be done all by hand here. And then there's more accurate So this is the flask of our tweeter that has to be machined to the 100th of a millimeter here. So that's all done on the in this.
It's a metal work.
Yeah, that's metal work. So very useful having all these machines, even if they're not used 100% of the time. We need them here. It's part of the equipment that's necessary. Now let me show you the next workshop.
What are these papers?
Aha, so these are papers we put. So we had an open day not long ago here, so we put these out to explain a few things to people. So this basically explains the evolution of speakers, sort of how we got to the speakers we have now that have three-way system or two-way system with all the specificities.
Explain us, please.
So here we have a closed system, okay, this is amplified, with an amplifier here. So the amplifier is perfectly adapted to the driver that it has to drive. So here we see in this column we have the frequency response. Here you see kind of the Q factor, you think of this as the distortion,
the damping,
and the phase. Okay, so one of these drivers is very good, but only in a small range of frequencies. Below that, it's not very good. So higher and below that, it's not very good, and it's compensated with some distortion. So you can see it's got quite a bit of distortion outside of this. The phase is quite clean. There's a bit of rotation in low frequencies, but then not much. Yeah. So how can you improve? This is basically the problem. You want to have a wider bandwidth, so you can improve in the high frequencies by adding another driver that's specialized in reproducing high frequencies here. But then you have to send the high frequencies here and the low frequencies here that you do with a crossover filter. So this is what you call a passive crossover filter.
Yeah, because it is later than the amplifier.
It's after the amplifier, exactly. In the amplifier, you use the same amplifier for this driver and this driver, but you manage to fill in this gap here and go high in frequency, but the filter adds quite a bit of distortion here and also phase rotation here. So then the next thing is you can have an amplifier that's perfectly adapted to the driver that it's going to be driving. So you have an amplifier that's perfectly adapted for the tweeter, that's normally an AB one, and here class AB, and then a class G amplifier for the woofer here, and then you have a high pass filter here and a low pass filter here. So you have much less distortion here in the crossover range. Now you still want to go lower in frequency, and this is where we add the port here. Yeah. So basically, instead of you're just using the front of the membrane, not the energy that goes to the back. And here you're using the front, that's perfectly accurate, but the back, you want to use it so that it perfectly fills up in frequency the lower end. So there's the resonance frequency of this system that's a mass of air in the port, and a spring that is the air in here. So it's basically like a Helmholtz, and this has to be perfectly tuned to be able to fill in this gap. So basically here you have the sum of what comes out of the tweeter, the woofer, and the bass that has to be totally flat. This doesn't change anything here to the distortion, and it doesn't change anything to the.
But in phase you have the problem because it is not aligned.
In the very low end of the phase. Yeah. Then we come here. It's a bit higher, but
this is the 5 system.
Yeah.
This is the continuum.
That is 4, and then we're going on to number 5. The next step is a damping system. So unfortunately, a driver like this one will not move exactly the same way at all the frequencies. So you can't just excite it and get it to move, because it's got a resonance frequency where it'll move much faster than other frequencies, and it has resonance frequency of the material itself and all these things. So you have to dampen it, and you have to dampen it differently at different frequencies. So this is where we've got a feedback system that measures the speed of the coil inside the magnet, and feeds back and acts through also a kind of EQ that gives the inverse function of the physical parameters of the driver itself, and then you can it acts on the output impedance of the amplifier. That's why we call it an adaptive output impedance system. And basically this will take out any of the ringing or distortion that can be due to the physical parameters of the driver. Mainly.
It's like a damping factor, the relationship between the output impedance of the amplifier, the R, and the impedance of the membrane, the zeta.
Yeah, exactly. That's exactly it. Yeah.
Yeah.
And then you can see here we've symbolized a little bit the EQ that goes through it.
Yeah, because you need to implement for different
frequency ranges.
Yes.
Different, yeah. So here we've solved this issue and we're left, so we've got a good frequency response, we've got a good damping system with low distortion, and we still have to solve
the phase.
So here again we have phase compensation. Basically, so what is phase? It's the time domain, and especially if there's a delay between the high frequencies and the low frequencies. When you hear a snare drum, you go tack, you have all the frequencies, or it goes tack, you have all the frequencies there at the same time. The high frequencies in the t, the low frequencies in the a, tack, they all come out at the same time. Unfortunately, if you go through any filter, whether it's electronic, acoustic, or mechanical, they will affect the phases differently, and there will be a bit of delay on the low frequencies. So it's very important to be able to compensate this and align them again. Otherwise, instead of hearing ta, you will hear t, a. And that is not the same. You don't have the same sense of impact between ta and t, a. So anyway, this is why what we do is we have a compensated phase response. So we have a series of all-pass filters, and an all-pass filter will affect the phase without affecting the frequency at all, and it will affect a certain range of phase. So you need several of these to be able to bring this phase response to a linear response that corresponds to a delay, a constant delay. Okay, and then you can have it lower or higher depending on the delay that you can accept. We accept a delay of less than 1 millisecond. Basically, it's half a millisecond, and that allows us to compensate the phase down to 150 hertz. Okay, so just think of it as being many all-pass filters that compensate for the physical characteristics of everything that's in our monitor, so that you ensure that the phase is perfectly correct down to 150 hertz when it comes out acoustically, and that you hear ta and now te a.
Yeah.
Okay, and the result of all of this
time aligned.
Time aligned.
Yeah.
The result of all of this is that, okay, this is a phase rotation in a standard three-way system, and this is in our system where 150 hertz, it's flat above that. Now, we could correct lower, of course, but lower, first of all, you'd have to accept a longer delay. That's not very, that's not nice to have when you're doing recording or post-production. So we've stuck to, okay, maybe I'll just go here first. If you put a square signal in, a standard speaker, you will first have the high frequencies will start, then the low frequencies, then the high frequencies will stop, and then the low frequencies will linger on. This is a typical step response of a speaker. What we do is we will wait for the low frequencies and start them all at the same time. That's the phase alignment, down to 150 hertz, and they all start at the same time, and you have a much better square signal, even if the lower frequencies...
They achieve at the same time.
Exactly, yes. So here, as you see, we've had to wait half a millisecond. That's half a millisecond. It's perfectly acceptable. And that allows us to have this phase response down flat, down to 150 hertz. We could go lower, but it would mean a longer delay. So that's the kind of compromise. And why we chose this is, first of all, because 1 millisecond is acceptable, or underneath 1 millisecond is good. And the other thing is that we're sensitive to phase between, say, 200 and 300 to 2 or 3,000. And that's because below that, the wavelength are so much longer than the distance between our ears, we can't hear the phase difference between one ear and the other. And in the high frequencies, the 20 centimeters we have between our ears corresponds to many cycles in high frequencies, so you can't detect the phase difference. There's many cycles in between your two ears. So you should think of the phase, we're very sensitive in this kind of area. So this is where it should be flat.
And this sorry.
Yes?
This phase shift is due the bass reference port, the headphone?
No, this will always, there'll always be due to all the system in here. There's always be a rotation.
Okay.
You'll have also this rotation it's due also to the speaker itself that has this rotation. There's a high pass in the speaker, in the mechanical system of the speaker.
Okay.
Yeah.
Okay.
So yeah, this is everything that's done in our electronics, and it's all, I mean, you can see what goes into an all-pass filter, and we have 14 of these that have to be in our three-way system. So all of the components have to be perfectly and accurately matched with a very simple design, so you minimize the components. It doesn't make anything easy using analog technology, but if it's done properly, it has some great advantages. Yeah.
Mm-hmm. And this is the AVIA.
So this is the AVIA. Maybe I can explain very quickly. So one thing to understand is that yeah, it's probably not the best way of playing it. But anyway, what we can see is that you have pressure going up and down. No? That's sound. That's what we hear. That's what we measure. That's what we try and reproduce. Is the pressure? Yeah.
Mm-hmm.
SPL is pressure. But we never talk about the associated velocity. When you have pressure going up and down, you also have movements of molecules going back and forth. Yeah.
Mm-hmm.
So this is, and it's counter phase. So what you have to, energy conservation dictates when the velocity is high, the pressure is low, and vice versa. So typically, when you're against a rigid wall, the velocity is 0. Yeah.
Mm-hmm.
And that's where the pressure is highest.
Mm-hmm.
And when you have a room mode, unfortunately, is when the half the length of the wavelength corresponds to one of the dimensions of the rooms, you'll have an echo and it'll start echoing like this. So you'd have the first mode, second mode, third mode. Yeah, that's quite the system. In a typical room like a studio, these modes are very bothering up to about 150 hertz, I would say. Mm-hmm. That's the kind of Schroeder frequency when they're disturbing. Above that, there's so many of them, you don't really hear them and they're not
Mm-hmm.
bothering. So that's a problem. When we make our very accurate speakers, you put them in the room and you have all these room modes that give you a frequency response that's really like this, and then also the RT60, it'll be, sorry, I'm just blabbering on. But what's important in a room is that I'll just continue here a little bit more. So, solutions for room modes, yeah? So you have the recording room and then you have the reproduction room. So of course you can EQ and take out these room modes. So the frequencies that resonate in the room, you can take them out. So this you can do, you can't do very easily with a drum. If it's an acoustic instrument, there's no way you can EQ it, can you? Mm-hmm. Okay, but when you reproduce it, you can go through a EQ and you can take out the frequencies that resonate so that at your ear you don't hear them anymore. Mm-hmm. But it'll be somehow the signal will also be wrong and distorted. You have bass trap. Bass trap is just a passive trap that works very well. The only problem is that it's bulky and it's either it's very bulky or it only works on a certain range of frequencies if it's a resonator. But it works, and this works on acoustic instruments or on reproduction, no problem. Then you have what you call noise cancelling, where you can make a noise and then you can cancel out certain frequencies by emitting the opposite frequency that will cancel out at the place where you're hearing.
The inverse.
The inverse, yeah. So here you can do that with live music or also on a recording. What you see here is that it'll work very well, but only at one position. Anywhere else it'll be worse. But it does work, and it works very well when you're only doing it in one position, typically in headphones. Mm-hmm. Noise-cancelling headphones, the distance between the speaker and the ear is always the same. It's very easy to cancel out. So what we do is it's like a passive absorber, but it's extremely efficient. It absorbs a lot more than any passive system, and this down to 15 hertz. So between 15 and 150, where you typically have room modes, they're absorbed. So anyway, how it works, very briefly, is what we're doing is we're going to impose a very low acoustic impedance in front of the object. So we have a microphone, we have this micro-perforated grill, and then we have this driver behind it. Yeah. So we will measure pressure, and this pressure we measure will dictate the movement of the driver. And the movement of the driver that's necessary to keep an acoustic impedance of about 100 Pascal per meter per second in front here. So what it's trying to do is keep inside this volume to keep a very low pressure and only speed. So this is why we call it a velocity absorber. And and outside you have so you're against a wall probably where you have high pressure and low velocity. And what we try and do is transform this pressure into velocity and then absorb the velocity. So the distance we have is only about 4 centimeters between the microphone and the counter reaction. That's why it's very important that all of this is analog.
Yeah,
it goes much quicker.
It's a low pass filter.
Yeah. And then...
And you integrate the pressure.
Yeah.
And transform to velocity.
And transform to drive this as velocity.
Wow.
So this is working as a source of velocity. Normally in a speaker you're driving it as a source of pressure, but here it's a source of velocity. Anyway, the result of all of this is that we're going to impose about between 100 and 150 Pascal per meter per second here in the corner, and then this impedance the impedance is the ratio between the pressure and velocity. And then this impedance will go up over about 1 to 1.5 meters to reach 400, and 400 is the same acoustic impedance as you have outside in the free field.
Yeah.
So basically what you see in the room is you see a certain surface here that's basically the portion of sphere of about 1 to 1.5 meters around the AVA, and this has an impedance of 400, so it's like if you opened the window of this size, and that's the effect it will have. So here you can see the equivalent absorption area of 1 AVA in square meters. So you should realize that 1 AVA is 0.2 square meters. So this is with the alpha Sabine of 1, it would be down here. And we are working in this area here, so basically between 2, that's already 10 times more efficient, up to 8, 9, 10 square meters. So it can be extremely efficient, up to 20, 25, we've even measured up to 35 times more efficient.
And the loudspeaker is vibrating and it is dissipating the movement in the absorber.
Yeah, exactly. So a lot of the energy is used up in the friction in this metallic grill, and then the rest is dissipated in here. There's very, very little energy. There's not much energy in sound.
Yeah, it will not use as...
Normally we should be recovering some energy as we're absorbing, but it doesn't work that sufficiently. So it's extremely useful to treat room modes down to 15 Hertz, and one of these has the same effect as a perfectly absorbent material of this size. That has to be very, very thick to go down to 20 or 15 Hertz. Yeah. We've installed these, of course, in studios because you want the sound to be very clean, but we've installed them in boiler rooms, heat pump rooms, technical rooms in hospitals. We've installed some in flats in London built above the underground. So any type of low frequency disturbance we can get rid of with rumble and that. I'll just show you here
the spectrogram.
Yeah, so this is basically, I think this is a good one. So here we can see that's a real example. This is Andy Hong in the US. So you can see this is his frequency response and the resonance in time, so the waterfall, yeah? So you can see that there's a few frequencies that resonate a bit longer. And then here with the AVA on, you can shorten all of this a lot more. Okay, and you can see that it also smoothens the frequency response.
Yeah.
So what Andy Hong said very accurately with this, in short, there was not enough boo in the bass, but way too much oom, clouding the overall image. Once we turned on the AVA, we could all hear the boom clearly, and everything else in the mix too, because there's less masking effect. So just another thing I want to show you is that if you have a listening position, for example, here, and you have your two speakers, first of all, the direct sound gives you an information on the source of the sound, what you're listening to. So it's very important that it has to be as accurate as possible. If you have a piano, you want to hear piano. You don't want to hear piano minus or plus some of the frequencies. So it's very important that the direct sound is as accurate as possible. And you don't want to change what's coming out of here just to compensate for your room, unless you can't help it. But this has to be direct. Then you have all the indirect sound, and basically the indirect sound gives you the information of the environment you're in. So it's important that this information on the environment you're in is balanced in all the frequencies. And the way we understand this is how long it echoes. So it's the RT60, that's basically the time it's echoing to go down by 60 dB. So what's very important in a room is that in the low frequencies, mid frequencies and high frequencies, this echo is the same. And it can be 5 or 10 seconds in churches. That's not a problem, it's balanced. Or it has to, but the problem in a church is if it's echoing for 10 seconds or 5 seconds, the message has to be very slow. That's why all the music and talking in churches is slow. In a studio, you want to listen to fast music, so the resonance time has to be much shorter. But it has to be shorter in the high frequencies and low frequencies.
Yes.
And often in studios, low frequencies are difficult to treat, so what we see normally is that in a studio, what you're hearing is you're hearing a very dampened environment, so as if you're outside with the high frequencies and as if you're in a cave with the low frequencies. Yes. And that is disturbing, not correct. Forget about having a flat frequency response here. It's not going to happen if you have reflections. If you're outside in an anechoic environment, you can have a flat frequency response. If you're in any kind of environment with echoes, you won't have a flat frequency response here, but it's not a problem because it gives you the sense of the environment you're in.
Yes.
Sorry, that was a bit long.
In any case, it is very difficult to have, even you have a very good acoustical treatment, it is very, very difficult to have a flat magnitude response.
Magnitude response, yeah. But anyway, this helps with these room modes that go in all three directions or diagonally. You can put the AVA where there's the most pressure,
in the corner,
and that's where it'll have the most effect.
Yeah.
Okay. So if you put it here, where there's a lot of pressure at 40 hertz, it'll have a lot more effect than if you put it here. Yeah. And this is basically the difference between the absorption, the equivalent absorption area. If it's in the bad place, it'll be like here, and if it's in a good place, it'll be extremely efficient. So this is why it's very difficult to say what effect it will have in the room.
It depends on the
room and where you position it on the room.
Yeah.
The only thing we can say is it's calibrated to be between 100 and 150 Pascal per meter per second. So that's what's calibrated here.
Okay.
Okay, back to manufacturing. So everything that's small happens here. So here we have a machine where we can make coils. That's very useful. We can make all sorts of coils, like these ones that we use as filters.
This is for filter?
Passive filters, that we use for Rowan.
An inductive filter?
Yeah, exactly. And then we use them also a lot for...
in which part of the system do you use? This is for the passive filters that we make for passive speakers. Rowan.
Okay. It's another brand that we manufacture here.
Okay.
So this is not used on PSI. Where we do use coils on PSI are for our tweeters that we manufacture here. So this is, you have a very small... So these we make here because nobody else can make them with as enough consistency in manufacturing, I'd say. So we have a coil here with a very thin wire. And this has to be positioned in a magnet, so we use a neodymium magnet here. So the gap in which it goes is very tight. Because to have a high SPL, you need high acceleration. High acceleration means low mass and high force. High force means high magnetic field. High magnetic field means small gap. That means that all the mechanical assembly has to be extremely accurate, like that. Yeah. So these we make here.
Indeed, the tweeter is like a little woofer coil, because
yes,
it works like a coil inside a magnetic field.
Yes, exactly. Yeah.
But there are other brands like use ribbon.
There's different ways of making air move, but we like this one for several reasons: directivity and consistency in movement and SPL, but there's different ways of doing it. But this is built exactly like a woofer or a mid-range driver,
And the magnets, the neodymium, are magnet here or in other side?
So these you can have a look at it. These we can magnetize here Normally what we do is we get them magnetized, and then we check them, so we measure them and saturate them also here, so we can also do them here. So these we can do, it's not a problem.
And the gap so small is to concentrate?
Yeah, that's so that the magnetic field that goes from the center to the outside, basically. The magnet is in the middle here, and it goes through here to here. So then you can keep a very high magnetic field inside, yeah.
Okay. Okay.
Quite simple, but it just has to be done properly. And careful. Bang.
And
So
this is
So this is what we use. Then the difficult part is assembling it perfectly, because it has to move up and down 20,000 times per second without touching anything. So this is the difficult thing, is positioning it right in the middle, that we do optically and also with sound. Also, when you can get it to vibrate, and then you can fine tune it inside. But this gives you anyway one of the, or we think one of the most. One of the tweeters with the best performance in the market you can ever find, that we use only on our products. Here we're transforming an electric signal into vibrations, and we do the opposite, transform vibrations into electric signal, and we build seismographs that measure vibrations
accelerometers.
Many bridges in Europe use our accelerometers, seismographs. Okay. Let me show you also. So I've explained
This is for wire for
the coils. Yeah. This one.
You have different sizes.
Different sizes for different types of coil we use. Yeah.
And there are some inductances.
Some.
Inductors.
Yeah. Here you can see different tools.
For the passive filters.
Yeah.
Oh, okay. Okay.
Talking about cables is extremely important, because it allows to conduct information. So we make all the cables here. It's what breaks mostly in domestic electronics is always the cables. So we make them all here. I'll just get to, and the way of getting the plastic off and twisting the thing and clamping the connectors is very important, and that has to be done. And so we do all of these here. And in 40 years, we've never had a faulty connection. And it's so frustrating when you have a radio or a Hoover and the connections break and you have to throw it away. So
the cables are clamped.
Clamped here. The connections are clamped here.
And not soldered.
No, they're clamped. The connections.
Why do you prefer the clamp?
Well, I mean, it's soldered if it doesn't move, but then when you have to assemble things, like from between the electronics and the driver, you have to put them together and then fix them. So there we use connectors like this.
But this fastener could be soldered.
Yeah, but then you have to do it. Then you can't take it apart again.
Okay.
So if you have to. We use these for the main connections, and when you have to build them, you have the electronic one side. You have to pull the cables through and connect it to the loudspeaker. And this holds and the connection is good, and it holds better than the soldering. So this is automobile industry standard. So it has to be able to vibrate for decades without breaking. That's the idea.
The components.
So here, let me just show. There's some elements that we buy, like these switches. Of course, we buy them, but they're not perfect for all the uses because they're not airtight. So these we have to fill them in with with some silicone so that they're perfectly airtight. Yeah. And here the same with these connectors. We have to fill them in here so that they're perfectly airtight.
Why do you need to seal?
Well, on our smaller monitors, the back panel is part of the cabinet, so it has to be airtight. The back panel.
To be sealed to the air cavity. Okay.
And the bigger cabinets, there's a board in between, so it doesn't have to be airtight. Now, as I was saying, everything we do on our speaker is analog, And the problem with analog is that first of all you need a smart and simple design, so you minimize the amount of components. And then you need, of course, a very tight control on all the components that are going to make it work the way you want it to. So we measure these all statistically, and some of the sensitive components we have to measure them one by one and match them. So these are the ones that are 1.1% above.
You match with a very low tolerance.
Yeah, because each board has to work. Each PCB has to really do what it's supposed to do with minimum error. So
so if you pair or match all the components, then all the loudspeakers are matched.
Yeah, the idea is that you can match. I mean, lots of people ask us, do you match speakers together? And we say, no, we don't match speakers together. We match the components and everything that goes on the speaker so that every speaker is matched to what we want it to be, the reality. And the advantage for this is that you can buy 2 speakers and buy a third one or 3 more for a 5.1. They'll all work together. And this is important for us, that they're done like this. Yeah. So all the electronics, are soldered here by hand. Gives you, I mean, this is also one of the smallest ones that we have, but we have all the different components here. The soldering is done by hand. The advantage, well, first of all, we haven't got the volume to do it any other way, but it also has the advantage of being able to adapt the soldering point to the component that's on the other side. And it also allows, a continuous supervision of all the production, and we can see basically supervise the quality all the way through.
So you put the PCBs here?
Then we put the PCBs here, and then sorry, I thought you were talking about the finished PCB so all the prints are done here.
Yeah, so put some prints.
We put the prints, you put the components on, you close it, turn it over, and then do all the soldering. So it takes about an hour for each one, yeah. Let me see if we can see some more here. So this is one for the smaller sub, so this is one of the bigger ones, but simple. And these are checked, so once we've done this, so this takes about an hour to do, and once this is done, we check them, so they go to be checked and pre-calibrated. I'll show you that in a minute. And then, when they're checked and pre-calibrated, then we put them on the back panel with all the power supply. And here you can see that the back panel is going to be part of the cabinet like this, and this has to be airtight, so all of these have to be airtight.
Okay.
That's why we have to check them. Yeah.
And is there any problem with the transform to induce some electromagnetic field into the electronics or into the coil of the woofer?
No, we don't have any problems with that. But it is one of the very sensitive parts that we use. So they have to be very good quality, and we have to check them. And we have had better ones and worse ones in the past, but now we control them properly. But the design, they have to be a certain distance, and they have to be mechanically very well manufactured. Otherwise, they can create noise. And if you do have, and it depends also, they can be sensitive to power supply also. If you have, if you don't have very clean power supply with other frequencies in the power supply.
Yeah, you must to have a clean.
Yeah.
So otherwise, harmonics, noise.
All the harmonics that are in there, yeah. And if there's DC also, but otherwise they're very, very good, and there's a lot less interference than if you have other types of supply.
The man that solder all the components must have very good skills, because
yes,
there are a lot of components only in 1 hour.
Yes, well, he does 8 of them at a time, and he puts all the components on all 8, does the soldering. So there's some operational procedures that tend to make it faster.
He's soldering the same component in all the cars, And then the next component, build the guards.
The way he does it is because what you do is you have it this way round, and then you put all the small components, the low components on. So you put all of these components on, kind of one, but so one of them will probably go here, here, here. So he puts all of those ones on. Then he goes the next, goes here, 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 and then when all the low components are positioned, then you put the top on it, and you swivel it over, and then you can do all the soldering of the low components. Then you put the slightly bigger ones on, and you start again. Then you put the bigger ones, because if you put these big ones, these ones wouldn't stay in position.
Yeah.
So there's probably about, I think, six steps of soldering. Yeah, but many more steps of positioning.
But he puts all the small components and
Yes,
and go upside
then
down.
swivels round. Yeah.
And then put the other
And then at the end he puts the biggest ones. Yeah, when all the other ones are already soldered and stay in place.
Okay.
It's quite simple, but it has to be done like everything. It's simple things that have to be done perfectly.
Yeah. Yeah.
Okay, let me show you the. So this is where we assemble the speakers. So here we have our semi-finished or semi-products, or not finished products, or work in progress, or whatever you want to call it. But we basically have the back panel. So this is the A25 with all the system here. So this is pre-calibrated and ready to go. We have all the speakers here.
Pre-calibrated because you adjust the trimmers.
So here we adjust the electronics, so that all the electronics are clean.
And how do you adjust the electronics?
There's quite a few tests that we do here. So there's 19 different steps that we do, and we can check.
But there are not trimmers.
Yeah, there are trimmers here.
But only two?
No.
Okay, I see. I see. This one.
Yeah.
Okay.
So that's pre-calibrated for the electronic, and then we have to fine calibration will take into account the exact driver that you use and in the cabinet.
So you adjust the electronics for all the woofers?
Yes. In the anechoic chamber, so first we pre-adjust the electronics, and then the electronics go in a cabinet with the mid, tweeter and woofer, and then we have to calibrate again.
Again?
Yes, that's the final calibration. Yeah. When they receive their calibration curve and everything.
Okay. So there are two calibrates.
Yeah, there was a pre-calibration of the electronics,
yeah,
and then the final calibration of the final product.
Okay, and the final calibration is with this?
Yes.
One more time?
Yeah.
Okay. Okay, and this calibrates
and the
all-pass filters?
No, the all-pass filters are clean. These are mainly adjusting the levels of the different drivers.
Yeah,
and there's also some trimmer points.
Yeah,
exactly.
Okay, and this is the woofers?
So these are the other drivers that we don't manufacture here because there's specialized companies in all the gluing and. But we check everything, so it's our conception, our design, but we outsource this and we check every single one when they come here. And we have between 10 and 30% that are not conform to our specifications, and we have to either rework or keep for other uses.
And they have any tolerance to pass?
So we have tolerances that are tighter than the manufacturers can guarantee. This is why we have to check them all here, and we use and it's not bad. It depends on the batches, but it's anyway. It's still cheaper doing it that way than manufacturing them here. And what's important is, as I'm explaining, lots of people think that this is the secret of sound, but it's not this that makes the sound. It's the way you get it to move, and the way you get it to move in harmony with its physical characteristics, because this doesn't move the same way at all frequencies. There's a resonance frequency of this. This is a mass on a spring. There's the resonance frequency of this material itself, the suspension, of the spider, and all of this have to be taken into account when you get it to move. So this is one of the reasons we have our adaptive output system, that impedance system, that adapts this, that dampens it differently at different frequencies. Yeah. So it's not this that makes the sound, it's the way you make it move. Whether it's plastic, paper, some kind of exotic material, you still have to dampen it properly so that you don't hear the material. It has to be light, rigid enough, and the physical characteristics have to be homogeneous all the way around. And yeah.
And for studio, the material is plastic, but also in paper.
So paper, the advantage of paper is it's a bit lighter.
But you have all other woofers or made of?
No, we use since we've made, so the paper's lighter, but with active we don't have really too much of a problem. So we prefer the reliability and the durability of the plastic. So since we've been making active speakers, we've been using plastic, and we haven't had any single problem apart from accidents. Whereas the paper and foam, they tend to they don't last as long, especially if they're exposed to the sun. So yeah, very, very simple ferrite, but correctly dimensioned. Let me show you the cabinets.
Yes.
That's all made here. I'll take the red one out. So this is the 7. So this is MDF. So this is wood.
Yes.
Bits of wood agglomerated, so stacked together. So mid-density fabric, and this is one of the best materials for acoustics cabinets. It absorbs. It's quite heavy. It absorbs vibrations in all directions the same way. It's quite cheap. It's affordable. You can machine it. You can paint it. Most high-end speakers are all made out of MDF. And those who want a perceived value a bit higher than MDF would put some kind of veneer or something that looks a bit nicer on it.
Did you ever try other material?
Yeah, we did try. We have tried other materials. We would still, to be better than MDF, you have to go into ceramic and cement or things like that. And that we'd like to do one day, but it's quite complicated. The only problem with MDF is you can't cast it. You can't make a mold with it. So when people start producing more, big quantities, they'll go on to plastic or cast aluminium, where they can mold it and have much bigger production volumes.
But it is not better, for example, to have cement concrete, because it will opposite to the movement of the loudspeaker, do it to the extra mass.
Well, it's heavier, so there's an opposite. It's a bit better cement, yes.
Yeah, but why not to manufacture with concrete, cement?
Well, because it's very heavy, it's fragile, it's very difficult. Very difficult to hold and make things like this with it. But yes, it's possible. Yeah. But the advantages of cement are not that great acoustically, compared to the disadvantages on the other side. Yeah, yeah, and this works very well also, MDF with and you dampen it inside. So these are also made 500 meters from here. So when we say Swiss made, it's really 95% of the added value within 500 meters around.
Yeah, because all these loudspeakers, all the elements are made here except the woofer.
Yeah, exactly. Yeah, and some of the parts like switches and things like that.
Okay. And the electronic components.
Yeah, well, they come from wherever we can get them, from the States, from Germany, from Asia. Yeah. And then we take all of these and assemble it here. So this is a series of 17s that have just been assembled. So there's the electronics, the drivers, and then there's the damping that we can see that's inside. So we have glass wool and.
Do you put a lot of porous absorber inside?
Well, the right amount.
And how much is the right?
It depends. It depends where. So in the smaller ones we have this type that's not too absorbent, but because we don't have too many echoes in the resonance inside. But in the bigger models, especially the floor standing, which is higher, you have to use a combination of both of them. For different reasons, because you have to position the very absorbent one in the right place, and you use the other one to sort of position it properly. It's quite an art, and there's a specific way of putting it in and a specific position for also again for all of these, and that's again trial and error and measurements that allow us to find the best position. Yeah. Yeah, I mean, we've got technology, but a lot of what makes our speakers so good is also all of our know-how in things that are quite simple like this also. The machine, you asked if we magnetized our magnets. This is the machine we can use to magnetize and also demagnetize magnets.
But did you use?
Yeah, this we use. Yeah.
Really?
Yeah.
For the
Not these ones we use to check them and check some of them. Yeah, if they're magnetized properly.
only for check.
Yeah, but we did used to use them for the tweeters we get. Basically, we can buy magnetized magnets or non-magnetized magnets. It's the same price, so we buy them magnetized and we just check them.
Okay, so only it's for check.
Yeah.
Okay.
But the previous batch we had was non-magnetized magnets, and we magnetized them here to make sure that they're saturated properly. Yeah.
And a question:
Yes?
How did it work with an electric field, an extremely large electric field, or how do you magnetize?
Well, basically, you fill these containers up with electricity capacitors. Yeah.
Yeah. Electrostatic.
And then you empty them all in this coil, so the electricity is going to go round and round and round, and this creates a magnetic field as it goes.
Okay.
But this will happen in a fraction of seconds. So the power that's delivered in a fraction of seconds is comparable to a train engine or something like that. Yeah, and this will create a strong magnetic field in the middle, and you can put your magnet here, and this will align all the little magnets that are inside the ferrite and make sure it's completely saturated, and it becomes a permanent magnet.
And it is permanent, the magnet induced?
Then it's a permanent magnet.
Okay.
Different types of alloy have different temperatures where they work and where they lose their magnetization, but the idea is that they become permanent. Yeah.
And do you use electrostatic, so a continuous electrical field, not variable in time?
No.
Fixed,
very quick. Yeah.
Okay.
And now the laboratory. This is where we check all of the prints. I showed you before. So the prints with the with all the components on it, and we check all the prints and pre-calibrate them. And it's also very useful. So we have all these devices that are quite old, but they work very well. And the new ones are not more accurate. The new ones just have more features to it. And then, of course, as the aim of a speaker is to transform an electric signal into an acoustic signal. So this is exactly what we do, is we inject an electric signal and measure the acoustic signal that comes out. So we do all the frequencies, so it goes whoop, and then you want to measure what comes out of the loudspeaker and not the echo in the room. That's why you need an anechoic room to measure it. So we measure them in here. So every single speaker produced comes in here. We inject a signal in here and we measure with this Brühlenkier microphone, laboratory microphone, what comes out. Okay, and this room is anechoic down to about 40 hertz, and we know the response that there is below that, so we can compensate for that. This is, if you don't have a room like this, I don't think you can seriously be designing and manufacturing speakers.
And why only 40 Hz and not 20 Hz?
Well, we could go lower, but it would mean 40
Yeah.
hertz, 20 hertz. You'd need double the
The space.
the space.
But this loudspeakers goes down until
Yeah.
20 hertz.
Yeah.
So
But then we know the response of the room and we can correct it.
Okay.
So it's a kind of compromise. And here we're equipped with a subwoofer here. So the subwoofer is when we calibrate the AVAA. So we put it here and we make low frequency sound and then absorb it, and we can measure it, and we can measure the acoustic impedance in front of it. Most important room in the factory. And then let me
And this is the
yeah.
response, frequency response, harmonic distortion, non-harmonic distortion, and response in phase.
Yeah, that's what we measure.
Response. Yeah.
We measure all of these and check them, and then we print out the frequency response. Let me just yeah, we have one here.
Okay.
So any precision instrument has to be calibrated and is delivered with its calibration curve. Any measurement instrument, medical, physical, whatever, it all comes like that. Yeah, yeah. Let me just show you quickly what it looks like. So this is typically the A25. This is what it looks like. This is the reference that we have. So this is the frequency response that has to be in between these two lines. Those are the tolerances that are tight, 1.5 dB, and it means if it touches, there's something wrong. It doesn't pass. This is the harmonic distortion that has to be.
This is the mask.
Yeah, that's the mask. It has to be under that. And this here, we're 90 dB. We have to be 40 dB underneath. This is the non-harmonic distortion. Very low background noise, but if you have if it's not airtight, or if you have something that's a rub and buzz, you'll quickly see something picking up. So it's very, very, very useful to check things like that. There's things that you don't see in here that you can see in here. And then this is the phase response, where it has to be around 150 hertz flat. And this is done for every single.
This is the crossover frequencies.
Those are the crossover frequencies, and there's different trimming positions you can do, and
with this, these are the frequencies when you can adjust.
Yeah. So basically, a lot of it happens in the mids and highs.
And you send this to the owner of the loudspeakers.
The top one only.
Okay.
The top one only, because that's what people understand, and it looks like. Well, let me show you one here. So this is a pair of. So this is what it looks like here. So it's printed and it's signed and it gets its serial number. Its birth certificate, we like to call it. Yeah. And this, when people come back and say, I'd like to check my speakers again, we check them 15, 20 years later, it doesn't move.
No deviation?
No. Even the older speakers, because the passive ones, we also used to measure them like that, and we have all the curves. So even those that are 35 years old, we check they don't move.
But they have capacitors inside?
Yeah, there's the passive filters and stuff. Yeah,
but the capacitors.
Yeah, there's less problems with that. No.
Okay. Sonometer?
Yep.
And do you use for something?
This we don't use. Yeah, just for research and development mainly. What I was going to show you while we're here is the AVAA.
Yes.
So the way we calibrate the AVAA. So yeah, this is another prototype that we play with, and this allows to position the microphone in different places and to use different types of grill. But that's basically it. But each one of them is calibrated. Acoustic impedance is calibrated, so we have to measure the pressure and the velocity of the air. So the velocity of the air is very difficult to measure in low frequencies. So we developed a a device here.
A ribbon microphone.
It's basically a ribbon microphone that we use, that we've adapted specifically
because it measures the velocity.
It responds to velocity. Yeah, exactly. So we have the pressure sensor here. It's a standard microphone, and then the ribbon microphone that we had to adapt for this. And then you have to calibrate.
The reference is pressure is an omnidirectional.
Yeah. Yeah, in these low frequencies, it's not a problem. It's the same as we use in the AVAA. So that's what we use, the measurement instrument that we've had to develop to calibrate the AVA. Now you have to calibrate this. So you need a source of velocity that's perfectly accurate, and we developed this device here. That's not very complicated, but it still works very well. So you have two drivers that will work like this, and we know exactly how at what speed they're working, and we can even put an accelerometer here so that we measure and we can check this speed. So we know the speed here, and you can put this ribbon microphone in here to calibrate that. So what I'm trying to say is that when you develop a new technology like the AVA, you have to develop the way to measure it and the way to calibrate the measurement instrument, so that you know what you're doing. Yep. And then the AVA, if you put it in one room or another room, it will perform differently because there's different pressure areas and things like that.
But the AVA is measured inside an anechoic.
Yeah, the AVA, so the impedance is measured there. And we know the impedance, but we don't know how effective this impedance will be in a certain pressure area. So we've developed...
So for what do you use this
That's to calibrate the impedance. So the impedance is pressure and velocity.
Yes.
It's pressure divided by velocity.
Do you use for calibrate the AVIA?
Yeah.
Okay.
Yeah. So to calibrate the speakers, we have our frequency response. To calibrate the AVAA, we have our impedance response.
And you put this microphone inside the anechoic terminal?
Yeah, in front of the AVA.
Okay.
So you have the AVA, and you can put it here, and you can measure in different places in different directions.
Okay. And you use a subwoofer to
create the pressure.
Okay.
Yeah.
Okay. That's good.
And then we can put it in a room. We've got a standard room that we use. That's a very small and rigid room here. And here you can adjust the room modes by putting this low or high and adjusting it.
Okay.
So we can create different type
frequencies.
of resonance frequencies in here. Yeah. This is what we use to test all the drivers when we receive them. So we have different ones. This is for the tweeter, so we put it here and we measure it. So before mounting them, we check that they all correspond to our specifications, one by one. What else can I show you? I'll just show you. So we finished the process. Here we're measuring drivers. So we
you put it in the box.
Yeah. Well, that's a special one. We'll measure that in the anechoic chamber. This is where we do all the packaging. The last human eye on our products before it goes out to the customer, where it will stay for 30-40 years, so it's very important that it's all nice and clean. And then we have a bit of a storage area I can show you also. So here we have raw material and finished products, and we have enough space here to work properly. Yeah, this is where we prepare the shipments that leave in the evening, so they've already left today. Yeah. Voila!
That's all, folks.
I think that's all, folks. Another thing I wanted to say is that we're very open about what we do. As I said, we've got certain technology that is not rocket science, but it's still quite advanced analog technology.
Yeah, I see Christian working.
Yeah.
These designs cannot be by anybody in the street.
No, of course. And there's a lot of know-how. What protects us, I think, is the know-how we've accumulated over 40 years.
Yes.
and we're very happy to show people how we work and what we do in testing. So we do welcome visitors. That's what I was going to say. So if anybody wants to. So thank you very much for stopping by, and appreciated meeting you, and I hope we'll meet.
Next time I will come with a van and I will get a lot of loudspeakers for Spain.
No problem.
Okay.
With pleasure.
Thank you, Fabrice.
Thank you, Fabrice.
Our cameraman. And thank you, Santiago, our lightman.
Thank you.
So, that's all, folks.